let's welcome Wanxin from the Department of AAE to present on control-induced learning with applications to human-robot autonomy.
So good afternoon, everyone. My name is Wanxin from AAE department. Today I'm talking about some of my work in my PhD study, the control-induced learning with application to human-robot autonomy. So over the past decades, increasing number of stories about progress in various robots, or more broadly, the autonomous system. If we just stand in a high-level perspective, and we can basically say that the autonomous system can include the following basic typical aspects: the task objective function, the dynamics, the policy, which finally leads to the behavior of the system. In the research domain, achieving the greater autonomy of this kind of system is a long-standing goal of not only for the machine learning community, but also for the control and robotics field. So in general, machine learning tries to achieve aspects of the system for the experience data. So a typical paradigm is we throw tons of experience data to train a generic models, for example, a deep neural network, to enable the robot to make optimal decisions and predictions. Although the learning methods show great potential to achieve the greater autonomy of the robot, but the main drawback of the learning method is it usually suffers from the low efficiency because of the data complexity and the huge computational complexity. On the other side, we have the control method, which has long established to provide tons of the structures, model theories to enable us to model the system, to characterize the behavior of the property of the system, or to synthesize and design the control for the system for the challenging problem. So this leads us to think about a fundamental problem. Can we make use of the rich structures, models, theories from the control theory to embed them into the learning method, in learning process, to design new learning algorithms that can achieve the higher efficiency, more good explainabilities, and the certificate learning performance? This is what we call the control-induced learning. In another perspective to understand the control-induced learning is by using this graph, where the x-axis is autonomy, a level of autonomy for the robot or the algorithm, where the y-axis is the data efficiency. We always want the robot to have the high degrees of autonomy, but to be very efficient to achieve so. But if we characterize different kinds of methods, we can say that different methods can, allocated in different, position of this plot. Our control-induced learning is try to integrate the models, the structures from the control theory and to promote the efficiency of the learning algorithm while maintaining the high degrees of the autonomy of the algorithm. And the other direction I focused in my PhD is learning with human in the loop, which basically aims to involve the minimal human factors into the learning process to achieve a higher, even higher efficiency with little sacrifice of the autonomy. So this is the two parts of my PhD work. And the first is more about the theoretical work about the control-induced learning methodologies. The second part is some new techniques about the learning with human in the loop. For the first part in this presentation, I will not cover all the methods. I will just particularly pick one, which could be an interesting one method we have published in the Europe 2020, which is called, we name it Poisson differential programming. Okay. What is Poisson differential programming? So let's give some backgrounds. Let's recall the building blocks of the autonomous system with the three aspects. Over the past decades or the centuries, the control community and learning community have proposed a lot of methods to try to achieve these three aspects of the autonomous system. But if we just take a unified new perspective to look at learning different aspects of the system, we can basically say, okay, learning different aspects of the system can be considered as the same problem, with all the differences what aspects of the system you are parameterized, and how do we define the loss function. I will explain in the following slides. Okay, with this big picture in mind, I start with to represent this autonomous system using the optimal control model in the control community, and where I have parameterized both the dynamics and the control objective function using a parameter, a tunable parameter set. So you can use implement it using any deep neural network or any parameterization tools to do that. So the fact is, the given parameter theta, the model, the autonomous system model will provide a trajectory which optimize the control objective function subject to the dynamics, which this trajectory phi of theta is also an implicit function of theta, right? And so for a lot of applications, we will need to define a loss function to evaluate the quality of the trajectory. And so our base problem is as stated as follows: how do we tune the parameters in the optimal control model such that the trajectory, the produced trajectory phi of theta has a minimal loss? This is a fundamental problem which can cover a variety of learning and control tasks, as I will show you in the next slides. But for a specific learning or control task, one only need to do two things. One is to change the details of your parameterized system, and the other is give a specific loss function depending on your specific applications. For example, if you are dealing with universal reinforcement learning, you want to learn an objective function of an expert from its demonstrations. So you can use the parameterized system, optimal control system, to represent this unknown expert. Then you define the loss function as the distance, for example, as the distance between the produced trajectory and the given demonstrations. And when you are dealing with the system identification or learn a neural ODE equivalence, you are basically given the data of the input and output sequence of the physical system. You want to identify the dynamics of the system. So in this case, and you just trivially set the control objective function in the parameterized model as zeros, then this model just represents a bunch of the dynamics models. So then you define loss function as a prediction loss, which will penalize the distance between the predicted trajectory and your obtained input and output data from the physical system. And when you do this policy optimization or motion plannings, you can basically use this parameterized model by replacing the control objective function using a feedback control policy, parameterized feedback control policy, and then set the loss function directly as your control objective function. And this kind of problem can formulate the policy optimizations or planning depending on how you parameterize your control policy. Okay, as you can see, these basic problems can cover a lot of control and learning problems, but here is the problem. How do we solve this problem? How do we solve these complex optimizations? Well, to make our life easier, we can basically consider the complex optimal control problem using a green box. Okay, this green box just take input as a parameter and produce a trajectory, and then evaluate it by the loss function, right? And so we aim to tune the parameter to minimize the loss function. So the natural idea is to use gradient descent, just to take the derivative of the loss directly with respect to the parameter set, right? And then you do one step further and you apply the chain rule to the gradients of loss function, and you will result in 3 gradient terms. And then you can draw this computational block. As you can see, each update of the parameter theta has the forward path from the theta to the trajectory to the loss value, and the backward path, which is to compute these 3 gradient terms in order to assemble the gradient of the loss. Here, but as you can see, these 2 gradient terms are directly from the loss function, which is readily to compute because the loss function is given. The only challenge here is how do we compute the derivative of the trajectory with respect to the parameter theta? How do we compute this guy? This is a key challenge of this computational framework. This is also our contributions here. Recall that this trajectory is from an optimal control system. As a result of optimal control system, so this trajectory must satisfy the Poisson maximum principle, or PMP for short, which is given by its 4 equations, right? And so remember that our goal is we want to compute the derivative of the trajectory with respect to the parameter theta. So our first step is we propose to differentiate the PMP on both sides with respect to the parameter theta. This leads to the equivalence of differential PMP. And the second interesting thing is that we find that the derivative of the trajectory with respect to the parameter theta in the differential PMP is exactly the trajectory of a new control system. We call this new control system as an auxiliary control system. What this means? This means in order to compute the derivative of the trajectory, we just need to solve a new auxiliary control system. Let's put this all together into this framework. You can see just in the feedback loop, and I just add the auxiliary control system to compute this gradient of the trajectory. So this is the whole picture. So we call this whole computational framework as a PDP framework. And when you apply the PDP framework, in order to, in addition to the previous two tasks, you also need to set up the auxiliary control system. For example, in the inverse reinforcement learning case, the auxiliary control system is an iterative, it's an LQI system. And in the system identification case, the auxiliary control system is another ODE equivalence. And in the optimal control or planning cases, the auxiliary control system is a feedback control system. Okay, we apply the PDP to various tasks, including the inverse reinforcement learning system ID, control and planning, and we compare it with the state-of-the-art learning and control method. We find that the PDP outperforms most of the state-of-the-art. Okay, this is the first part of my presentation, which is techniques about constraint learning. And so next, I will talk about the part 2, which is some new techniques about robot learning with human in the loop. Here we have proposed, here the fundamental questions to understand robot learning with human in the loop. The first question is to understand how human can help in the robot learning. We know that humans are really good at contextual awareness. For example, humans know the task of the goals, know the environment, know the constraints, and also we know that humans are really good at giving the intuitive, explicit actions to a robot instead of just coding or programming a robot or writing down the math. Humans are more likely to willing to give the intuitive, explicit actions. So this fundamental, common sense to make us to think about how do we develop the robot learning with human in the loop. So in order to do that, we have two principles. First, in order to promote the learning efficiency of the robot, we just want to make sure that the algorithm requires as minimal human intervention as possible. And the second is that we want the human intervention should be in humans' mostly comfortable way, because we don't increase the human's burden. So along these two principles, so we have proposed two techniques. One is learning from sparse demonstration, the other is learning from directional correction. Here I will just talk about the second one, learning from demonstrations, learning from directional corrections. Let's consider the following case. Let's consider, okay, there is a robot, and the robot is controlled by minimizing a cost function, which is tunable and parameterized by the parameter state. And let's consider there is a human who is supervising the robot. And in humans' mind, let's assume there is a true cost function in humans' mind for the robot motions. But humans have no idea about what the true function is. But we represent the true function as the theta k, as the theta star. So what a human can only do is to make a correction to the robot as a following procedures. So let's assume that currently robot have its audience for his control objective function. So the robot will generate a trajectory, and then human observing the trajectory and think about, okay, that is not satisfactory because the robot objective function is not identical to my objective function. So what does it mean? So the humans will then provide a directional correction to a robot. I need to emphasize this is a directional correction. For example, if you are correcting a mobile robot, what you only need to do is to tell the robot to go left or right at a certain time step. You don't have to tell the robot how much left or right he needs to go. So we see the direction correction, which means the magnitude of the correction does not matter at all. So after these corrections, the robot will update its control parameters to generate a new trajectory, and robot will correct it again. So this process repeats over again. So our problem is how they find update rules to the further updates that by taking advantage of the human correction, the robot can update itself such that it can converge to the convert to the objective function human desired, human expected the robot to do. So the first step to address this problem is we need to characterize the human's corrections, right? So we make a fundamental assumption to humans' corrections. We assume that humans' corrections always point to a direction that decreases the robot current motion cost. So what this means. This means okay, humans' correction direction is always filled in the same half space of the gradient descent. So after some derivations, this is equivalent to the Fulling linear inequality for the true cost function. So this is the coefficient of HK and BK determined by both the robot current motion and the human's correction. So before I present the whole picture of the algorithm, I will first describe the key idea of the learning from directional correction. So instead of the direct final updating rules for the robot parameters, for robot updates its parameters, we choose to maintain a search space, a parameter search space. And we want both the robot's current guess and the human's true objective function parameter are both in this search space. So if we can develop a rule to update the search space such that the volume of such space is reduced to 0, we can justify that okay, that at that point the robot current guess parameter is converging to the a human's expected one. So this is a key. This is the whole procedure of the learning algorithm. So let's consider we are currently have this search space omega k plus 1. Then we first let the robot to pick one initial guess from the search space. Let's say the theta k here, and then the robot will generate the trajectory by using the trajectory function, by using the objective function determined by this theta k, and then the human will apply the correction. And then these two informations can give us a linear inequality which determines the half space. And then we update the search space by intersecting the current search space and the half space determined by this linear inequality as our next search space. So this process will repeat over and over again. As you can see, the key learning method and the key learning process is to just cut and remove the search space until the search space is converging, the volume of search space is converging to 0. So here are some properties. I will not make the details, and but I will give the final theoretical results about this process. Is that when we choose the robot guess at every iteration, approximately at the center of the search space, in this case we choose the center of the maximum volume ellipsoid of the search space. And we can guarantee the upper bound of the decreasing rate of the volume of the search space. And so this means that when we choose the center of the MVE in the search space, we can guarantee that the volume of search space is decreasing exponentially. So then we can justify, okay, the robots as the iteration goes on, as the human correction comes in, and the robot current guess is converging to the human's expected one. So we have developed some computer games to allow humans to interact with the simulator through the keyboard. As you can see, this is I don't know whether it's okay. It works. So initially you can see the robot is moving but failed to tasks. As you can see, the robot give a correction by clicking a key and tell the robot okay to bend counterclockwise a little bit, and then the robot you can finally learn your objective function, learn cost function to achieve the task correctly. And also this is another game for the UAV flying. We just give the command of the UAV to go up and left forward, backwards, something like that. And finally, just for example, after say 7, I guess in this case 7 or 8 iterations, the UAV can correctly learn its objective function to finish the task. In this case, it goes through the door and landing on the right-hand side. Okay, this is the whole picture of the learning from directional correction. So, okay, this is a small summary of my PhD work, and yeah, I acknowledge the collaborator, especially my professors, and I'm open to any questions. Thank you.